G'day, welcome back to Mathematics. Today we are starting a new series where I'm going to go through all the 2024 HSC exam papers and show you a handful of questions that I think are interesting or that I think I can provide some insight on. Kicking off with the Extension 2 paper from 2024, of course. Now the Extension 2 paper has some multiple choice questions and then it has 6 question sets that are typically ascending in difficulty. So I'm going to go through one of the multiple choice questions and then I'm going to pick one question from each of the 6 question sets. And so the last question will be a real spicy one, a nice little band 6 question to get you fired up on whatever day it is you're watching this. This is in preparation for your trials or your HSC. I wish you good luck and let's dive right in with the multiple choice question. Okay, this one is question 6. It's a pulley question and there have been a couple pulley questions in recent years, so these are definitely fair game in terms of NESA. We have a light string, light means no weight, attached to 2 weights through a pulley. This big one is 9 kilograms and this one is 5 kilograms. Acceleration due to gravity is g, and we're asked to find the acceleration of the 9 kilogram mass. Now, I really like these pulley questions because if you haven't seen them before, they can be really confusing, but once you've done a couple of them and you've seen the correct method or the correct approach to these, they're actually really simple. We're going to start off with our force equation, force equal to mass times acceleration. Now we're going to use this equation to figure out what the acceleration is. So all we need is the force and the mass to achieve that. So let's think about our forces. This 9 kilogram weight will have a force working downwards. That's going to be mass times acceleration. So 9 times g. Okay, 9g going down. Now this 5 kilogram mass will have a 5g force that's going down this way. And that force is going to pass through the string and it's really working up this way. Okay, so the 5g for this block that's going down this way through the string is really working up if we're thinking in this dimension over here. So if we take down to be the positive direction, we can say that the resultant force on the 9 kilogram mass is going to be the difference between the 9g and the 5g. So we've got a resulting force of 4g in the down direction that I'm taking as positive for this question. Okay, so 9 going down, 5 pulling up, giving us a resulting force of 4g's. Now let's put this into our force equation on the left-hand side. That's our resulting force. Now let's think about the mass of this object. Now crucially, these 2 blocks are joined together by a bit of string. So because they're joined by string, they're actually one object. Now the string has no mass, it says light. Now the total mass of this object, which is the 2 blocks connected by string, well 9 plus 5 is 14. So we have a total mass of 14 kilograms of this entire object. Okay, putting that into our equation, we're putting the force on the left, which is the 4g. We're putting the 14 here for the mass. And now all we need to do is solve for acceleration by dividing both sides by 14. And then 4g divided by 14 simplifies to 2g over 7. And that's going to be equal to answer A, 2 over 7g. There we go. So like I said, as long as you know how to approach them, very straightforward, but you've got to know this trick of the 2 weights working against each other and the combining of the masses. Very, very crucial. Okay, let's dive into our first short response, which is in the first question set, question 11. This is typically where you find a lot of friendly band 3, band 2 level questions, and it's expected that we're going to get most of these right because they're usually pretty softballs. Here is a 3-mark integration question. We've got integration from 0 to pi on 2 of 1 over sine theta plus 1 with respect to theta. Now the only slight trick with this question is that it's not telling you which method of integration to use. So we are expected to look at this integral and recognize that this is a prime candidate for a t-value substitution. When you have a sine or a cos on the bottom of your fraction, or even both, sine and cos plus and together, it's a really good option to let t equal tan theta on 2. Hopefully you have some experience with this substitution. Of course, all the substitutions you're going to need are on the reference sheet. So we have sine, cos, and tan in terms of t. And so we're going to use these substitutions to transform this integral into an integration involving t instead of theta, and hopefully that will be easier. Probably should have mentioned this already, but the best way to get value out of this video if you're using it for study is to pause the question when I chuck it up on the screen, have a crack yourself, and then I'll run through my solution and see how it compares to yours. And if we're on the same wavelength, same answer, you get that free dopamine hit. Anyway, the only thing that's not on the reference sheet that you got to know is the substitution for d theta or dx. Okay, that's a nice little memorization trick the d theta, or the dx, is going to substitute to be the same thing as the sine expression, but instead of a 2t on top, you do a 2dt. And just memorizing that will save you a decent chunk of time. Okay, we've also got to change our limits. Thankfully, they're almost always 0 and pi on 2, which turn out really nicely, because when I do tan of 0 over 2, that's just tan of 0, and tan of 0 is 0. And when I do tan of pi on 2, half of pi on 2 is pi on 4, and tan pi on 4 is tan 45, which is 1. So quite often, we're seeing these limits turn into 0s and 1s that make our life easier. So putting all the information into our integral, we have our new limits of 0 and 1. We've changed our sine theta to be our substitution from the reference sheet, and we've changed the d theta to be our substitution from the memory bank. Now we're just going to proceed with this and tidy it up and then do some integration. Okay, so to tidy it up, the bottom of this fraction, everything's going to get multiplied by 1 plus t squared over here. That's really good because it's going to simplify this fraction here to just be 2t, and it's going to turn this 1 into a 1 plus t squared. So that's the whole denominator of the fraction being times by 1 plus t squared. Now I'm just going to yoink that 2 out the front and make this quadratic on the bottom look a bit more familiar. Writing it in this form is now very clear that it is a perfect square that can be factorized using t plus 1 squared. So we're going to do that. And now we can integrate this just using good old-fashioned power rule integration. We're just going to write this fraction as t plus 1 to the power of minus 2, and now proceed as you would normally. We're going to add 1 to the power, we're going to divide by the new power. We're also going to divide by the derivative of the function, but that's just 1, so I'm just going to leave that off because that's kind of invisible for today. 2 still out the front. Before I sub in my limits, I'm just going to simplify the inside a little bit by using a positive index and by bringing the negative 1 out the front, but that is optional. But here's how I would write it to make it look a little bit nicer. And now I can just sub in 1, sub in 0, and then calculate my answer. I think what's inside here turns out to be negative a half, and then negative 2 times negative a half gets us a beautiful answer of 1. So if you did a t-sub and you got to an answer of 1, congratulations on your 3% of the 2024 exam. Okay, stepping up now to question 12. I chose this one, which is a cool proof question involving integers. We have explain why there is no integer n such that bloody bloody blah bloody bloody blah is equal to 2 for 2 marks. Okay, whenever you're encountering an integer proof, a question talking about integers or n's or whatever in that, and you can't see a good place to start, it's always good to keep in the back of your mind that if we're working with integers, there's only 2 cases. It's either going to be an odd number or an even number, and that can often be a really good place to start, especially because I'm seeing an n here and an n plus 1 here, and so I'm thinking, oh, well, if n is even, then n plus 1 is odd. It's all hinting me towards using some facts about odd and even numbers. So because we don't know whether n is odd or even, we have to explain our way through this proof in 2 situations. The first situation, which I'm calling case 1, is we're going to assume that what if n is even? Okay, so if n is even, that means that n plus 1 is odd, and now we're going to think about what's happening with our powers and our 79. Well, when I do n plus 1 to the power of 41, I've got a bunch of odd numbers multiplying together, and whenever you take the product of odd numbers, the result is always an odd number. And now for the n to the power of 40, because n is even, n to the power of 40 is a bunch of even numbers multiplying together, which always gives you an even result. Now we're taking this even result of n to the power of 40 and we're multiplying it by 79, which is an odd number. So we have this is a product of odd and even. And whenever you multiply an odd and an even number together, you get an even number. So we have explained why the front part is an odd number, and we've explained why the second part is an even number. So what we have here is a difference between an odd and an even number, and anytime you do an odd number, take away an even number, it gets you another odd number. Now that's crucial because the right hand side is 2, which is quite clearly an even number, fun fact. And so here we've explained why the difference gets us an odd result, and therefore the odd result can't be equal to 2. So that's a fair amount of work, but that's only worth 1 mark. That's only one case. We now need to kind of repeat this process by considering, well, what if n was actually odd? Luckily, all the logic is very similar, and if you've done this one, the next part is just very straightforward. So case 2 now, considering that if n is odd, it would tell us that n plus 1 is even. So if we're doing n plus 1 to the power of 41, we're multiplying a bunch of even numbers, which gets us an even result. Now let's think about n to the power of 40. That's a bunch of odd numbers multiplying together, and that always gets us an odd result. We're then going to multiply this by 79, which is also an odd number, which is therefore still odd. I probably could have done these two in one step to be a little bit more efficient, but hey, I've already done it now. So what we have is this thing here, which is an even number, and this thing here, which is an odd number, and we're once again doing a difference. So we have even minus odd, which, as we already explained, is always equal to odd, and an odd number cannot be equal to 2, and therefore this expression can never be equal to 2 for 2 marks. So there you go. When you're stuck on an integer question, plan B or sometimes plan D can be just to think about odds and evens, and it can make your life a lot easier. Okay, into question 13 now. We're doing a mechanics question. This one is about simple harmonic motion. We have our acceleration equation here, negative 4x plus 1. When we are passing through the origin, we have a speed of 4 meters per second. So when x is 0, velocity is 4. What distance does the particle travel during a full period of its motion? Okay, if we want to find the total distance traveled during a full period, we need to know where our center point is, and we need to know how far up and down we're going, because this simple harmonic motion is just a wave. So we're just trying to find our amplitude so we can then calculate our wavelength, I suppose. So let's get some information. First of all, this question becomes much, much simpler if you know how to use this equation in red. Hopefully your teacher showed this to you. If they didn't, I've got a video on my channel that goes over this and does some uses with it. This thing in red is not on the reference sheet. It is going to be on the reference sheet in a couple of years, but for some reason it's not there now, so don't get me started on that. But this is an equation relating the velocity, n, which is related to the period, the amplitude, and the center, and the displacement of a particle or an object in simple harmonic motion. So it's going to be very useful. Let's look at our acceleration equation and see what it's telling us. Now we know we can write simple harmonic motion in the form of negative n squared x minus c, where n is once again related to the amplitude, and the center point in here is going to be negative 1. So by looking at the equation they've given me, if I know my stuff, I can be like, okay, cool, this tells me that n is equal to 2, and it tells me that I'm oscillating around the point x equals negative 1. So we have n equals 2, and we have center of motion negative 1. So we can put those two bits of information into our red equation here, and we get v squared is equal to 4 times a squared minus x minus 1. Okay, now this is also really good because I have some more information in the question that I can use about the relationship between x and v. As we already said, when we're passing through the origin, so when x is equal to 0, the speed, or the velocity, is equal to 4. So let's chuck that in. We have, on the left-hand side, velocity is 4 when x equals 0. So on the left-hand side, we have 4 squared, and inside here, we can make this equal to 0, and now the only remaining variable is a for amplitude, which is the thing we were trying to find to figure out our full period of motion. Okay, so simplifying this, we can just divide the 4 across the left-hand side, and inside here we have a squared minus 1. So a squared minus 1 equals 4. We can just add the 1 across this side and make that a 5, and then take the square root to get our value of amplitude. So amplitude is going to be root 5, but it's going to be plussing and minusing to our center point. So now if we sort of visualize what we're working with, we have, this is our oscillation. We are centering around negative 1, and we're going as far left as negative 1 minus root 5, and we're going as far right as negative 1 plus root 5. Center point plus or minus the amplitude. So to finish this off and find how far we're traveling through one full period, think about we're starting up here and we're going to go down, hit the bottom of the wave, and then curve back. So a full period is from the start point back to the start point. So that's going to be root 5 happening once, root 5 happening twice, 3 times, and then 4 times. So if you want to find the full distance traveled for a full period of motion, all you need to do is 4 lots of the amplitude, and the amplitude is root 5. So to get our answer for 3 marks, we have root 5 multiplied by 4. We have 4 root 5 as our total distance traveled in one full loop of motion. There we go. So if you know how to set up your equation and you know what to look for, you know what your letters mean, and this thing in red here makes this question an absolute piece of piss. Okay, on to question 14. Now we're over halfway. Wow, we're absolutely flying. Question 14, I think this is a really cool one because it looks very complicated to me at least. There's a lot of Z's and W's and some weird expressions, but with just some clever geometry and just knowing how to work with your equations, this is actually a very, very simple 2 marks. So let's break it down. We have the argument of the division of 2 complex numbers being equal to negative pi on 2. Now, we can break this apart. When you have arg of z over w, this is the same thing as arg of z minus arg of w, okay? The argument has the same properties as a logarithm. Don't think about it too hard because it makes your brain hurt. But this is just basically saying when you want the argument of the division of two complex numbers, it's the same thing as the difference in their arguments, okay? So this means the difference between arg z and arg w is negative pi over 2. So these two things are negative pi on 2 apart in terms of rotation. If that's too hectic for you, you can take all of these parts and you can multiply them by negative 1 to get arg w minus arg z equals pi on 2, which is a little bit more friendly and easy to make sense of in your head. So what could that look like? It means that if we had an axis like this with a real and imaginary axes, and w was something like over here, I know that the rotation from w to z, or the difference in their arguments, would be 90 degrees. So that means z would be somewhere over here with a nice little right angle between them, okay? Question wants us to interpret this information here as z and w being two vectors with a difference of 90 degrees in rotation. Now once you've got that, we can go to what we're actually trying to find, which is z minus w over z plus w magnitude, or modulus, I guess you could call that. Now, when you have the modulus of a fraction like this, if it's easier, you can split it up into two separate moduli. So we have mod z minus w over modulus, or length, of z plus w. So in terms of our diagram over here, let's think about what z minus w and z plus w look like. So we have z here and w here. If I just sort of complete the rectangle here. Now, z plus w is going to be the vector to the corner point of here. Okay, this is w here plus z here. So that black dotted line right there is z plus w. Now, if we want to find z minus w, this is the vector from w to z, which looks like this. So what we have here is z plus w and z minus w are the two diagonals of our rectangle. And a cool little fact about rectangles that you might have learned in year 8 if you were paying attention is that they are equidistant, okay? The diagonals of a rectangle are the same length, which means that these two moduli have the same value. And so dividing it by itself gets you an answer for 2 marks of equal to 1. So that's the second question we've done today where the answer was equal to 1. So I guess the moral of the story is here, if you're not sure what to do, you should probably just guess 1 and you might get lucky. If you did it in 2024, you would have got some marks. There you go. Okay, so the magic of geometry, the magic of a diagram, and the magic of knowing how to work with your expressions and know how to split apart your arguments. Fun little 2 marks, I thought. Okay, getting into the really, really spicy section now. Question 15 and question 16 are where the tears begin, but not for us today. Yeah, that's what I said anyway. Question 15, we have a really, really hectic band 5 integration question. It's giving us a hint of using a suitable substitution, and we're meant to sort of figure out what's going on here and get towards an answer. Now, reading the code of the integral, whenever a question says using a suitable substitution, and we're seeing a square root and a squared on the bottom of a fraction like this, we have seen these in exams semi-occasionally, like every few years, and they are indicators that you should be looking for a clever trigonometric substitution here. If this was something like 4 minus x squared, I'd be thinking about my trigonometric identities and being like, oh, well, if I had 4 minus 4 sine squared, I could do something with that. But the issue that makes this a really challenging question is the x here. So it tells us the first thing we've got to do here is try and tidy up the inside of this square root by doing a little bit of square completion. Okay, so we're going to try and make this look a little bit nicer to make it a bit clearer what our clever substitution is going to be here. So where we're going to start off is we're going to factor out the negative out of the x squared and the 2x, which looks like this. And now I want to make this a perfect square so it's nice and factorized and friendly. So filling in the gap, I obviously need a plus 1. And now because that plus 1 is really a negative 1, I'm just going to put another plus 1 over here to balance it out. So all I've really done there is add 0 because I've done negative 1 plus 1. Now just rewriting this, I'm going to put the 1 at the front and then do minus and then factorize this perfect square once again to be x minus 1 all squared. Okay, so a little bit nicer now, and it's a little bit more obvious that what's going to be really clever here is to let x minus 1 equal to sine theta. Or x minus 1 equals cos theta could also work, but I'm going with sine theta for today. Now, why is that clever? Because underneath here, 1 minus sine squared, using our knowledge from the advanced course and the trigonometric identities, 1 minus sine squared is going to be equal to cos squared, which is going to simplify with the square root. So it's a very, very clever substitution. If that was a plus in there, I might have had to use tan squared instead, or tan, but because it's a minus, sine theta is going to get the job done. Okay, so also worth noting that later on, we're going to need to change the x on the top, and x is going to be equal to sine theta plus 1 just by rearranging this. We also need to figure out the dx. We're just going to differentiate both sides of this substitution and say dx is equal to cos theta d theta. That's the right-hand side differentiated with respect to theta. And now let's chuck some stuff in and just hope and pray. So the top now becomes 2 times sine theta plus 1 squared. On the bottom, we have 1 minus sine squared, which of course is going to turn into cos squared. And then the square root is going to turn that into cos, which is actually pretty good because there's a cos right there, and they're just going to cancel out and make our life a little bit easier. So let's jump to that after we make a little bit more space. Keeping in mind what our substitution is, because that's going to be very crucial very soon. Okay, so the bottom, as I said, turns into square root of cos squared, which is cos, and then I've just yoinked the 2 out the front for now, but I think I'm going to bring it back in later, spoiler alert. Cos thetas cancel out, and while I'm doing that, I may as well expand out this perfect square on the top, so I have some stuff that I need to deal with, because I can't integrate this factorized, it's too scary. So expanding that out, I get sine squared, and then I get 2 sine theta, and I get plus 1. Okay, now sine theta and 1 are not scary to integrate. Sine squared is not too scary either because there's a nice little substitution on the reference sheet which you should have covered in the extension 1 course. We changed sine squared to be equal to a half of 1 minus cos 2 theta, and this is the calculus friendly version of sine squared. And now, because it's going to make things nicer, I'm actually going to bring that 2 out the front back in to turn this half into a 1, turn this 2 into a 4, and turn this 1 into a 2. So bringing it back in, we get 1 minus cos 2 theta here, we get 4 sine theta here, and we get plus 2 on the end. Now everything is nice and friendly. Now I can go and do some integration and then figure out where to go from there. The last part of this question I actually think is probably the hardest. Okay, moving across there, integrating everything. So 1 is going to integrate to, pardon me, I should have done 1 plus 2 is 3, and then 3 integrates to 3 theta. Cos is integrating to sine, and we're dividing by 2 because that's the derivative of the angle. 4 sine theta is integrating to 4 cos theta, and then the 2 is gone. Should that sine have integrated to a negative cos? I feel like it should have. Is that going to matter? It's definitely going to matter. And we're back. Okay, now where were we? Now, as everybody knows, when you do 1 plus 2, you get 3, and 3 integrates to 3 theta. Cos integrates to sine, and sine, crucially, integrates to negative cos. So don't forget that, otherwise you'll be very embarrassed on a public platform and probably bullied in the comments, deservingly so. Moving on from that, we are going to simplify this a little bit because we don't know much about sine 2 theta, but we do know some stuff about sine theta. So we're going to use the fact that sine 2 theta is equal to 2 sine theta cos theta. And that half is going to conveniently get rid of that 2 for us, so we get sine theta cos theta. Now, what I think is probably the most challenging part of this question, or the part that gave me the heebie-jeebies the most, is turning this answer back into an answer involving x's. So the sine theta is no drama because sine theta is x minus 1. The theta is not too bad because I can just do sine inverse of this expression and get theta. What about the cos though? How do I go from sine to cos without doing some calculations? Oh, I know, the magic of the triangle. Here is a triangle where sine theta is opposite over hypotenuse, which is x minus 1 over 1. So hey, it works. Let's use this triangle and figure out the adjacent side so we can get an expression for cos theta. Let's do the square root of 1 squared, take away x minus 1 squared, which looks like this. And this now tells me that cos theta is going to be equal to this divided by 1. So just this basically. So we have our sine theta, we have our theta by doing sine inverse of that, and we have our cos theta by using this clever little triangle here and getting this expression. Now we can chuck everything into our answer. It's going to look like an absolute dog's breakfast, but it is going to get us 3 marks, so we're not going to complain too much. Here is our expression. 3 times theta looks like that. We've got sine theta just there. We've got cos theta just there. And then we've got the minus, crucially, for cos theta on the end with the constant. I think from memory, this answer can be slightly improved because we can factor out these surd terms and simplify a little bit. But as you can see, I've run out of room and I don't really care. So this is definitely going to get you 3 marks, and that's good enough for me. So hopefully that's good enough for you. If it's not, like I said, bully me in the comments. I can handle it. Okay, let's finish off with the band 6er from the last question set. Worth 4 marks. We have a cos kx curve drawn right here. We have the value of k chosen so that a circle can be drawn with the center at the origin, and as we can see, the cos curve is touching the circle in exactly 2 places. And we have the circle is never above the graph. We have a point AB, which is right here, and it's A and B are both negative in the first quadrant, as we can see, and there's our setup. Now, the vector joining the origin to the point AB, so if we had a line from here to here, that line would be perpendicular to the tangent of the graph of the function at that point. Do not prove this. Don't you dare prove it, or you'll be greatly upsetting your marker and they might just burn your paper. Show that k is greater than 1. All right, let's dive into it. Let's move this across. Oh my God, that was awful. Sorry you had to watch that. All right, let's draw a vector. Here's a vector joining 0 to point AB, and let's look at let's look at the tangent of the cosine curve at that point. There's our tangent. I didn't draw that super well, but you sort of get what I'm going for here. Blue line and red line are perpendicular. Don't prove it. Show that k is greater than 1. Okay, so I'm seeing some tangents and some perpendiculars, and so that's really sort of giving me a hint here that I'm gonna have to use some goddamn calculus to get my way out of this. So let's start off by taking the derivative of the curve cos kx. Now, fortunately, I know that when you differentiate cos, you get negative sign, and we're gonna multiply by k. So there is our expression for the derivative of the curve. Now, let's think about how we get the gradient of this red line. Well, if you sub the x value into this derivative function, it's gonna give you the gradient. That's why we call it the gradient function. It's very appropriately named. So the gradient of the red line at this point, where the x value is a, the gradient is going to be negative k sine a times k. Okay, so we've got our red line gradient. Let's get our blue line gradient. Fortunately, if you watch this video, there's a massive chance you passed year 9 and you know that the gradient of a line is rise over run. So the rise is b and the run is a. So we have blue line has a gradient of b over a. Now, what we do know is that these two are perpendicular, which means I can take this blue gradient, which is b over a, I can flip it upside down and make it negative, and I get the gradient of the red line. So that tells me that negative k sine ka is equal to negative a over b. And now we have an equation and we can start to do some stuff with it. Something else that's really clever we can use is that some more information we have is that the curve y equals cos kx passes through the point AB. That tells me that when x is equal to a in this equation, the value of y is equal to b. So we have b equal to cos ka. That's really cool because I can sub that into my equation here, making a bit of room. And where I have this fraction here, I can chuck in cos ka for b. So there we go. Now we're trying to figure out some information about k. So why don't we just go ahead and make k the subject by getting rid of the negatives from both sides and dividing the sine ka across to the right. That looks like that. Okay, and now is where things start to get a little bit more tricky. We're going to simplify the fraction because whenever I see a sine and a cos multiplying, my extension 1 flashbacks start going off and I think, oh, I can turn this into sine of 2 theta, using the fact that 2 sine theta cos theta is equal to sine 2 theta. So I'm going to multiply top and bottom of the fraction by 2, so I can then turn the bottom of the fraction into sine of 2 times the angle, so sine 2 ka. Okay, and now it'd be really cool if I could get rid of the sign off the bottom. So we have to get really, really clever now, and we have to use a little bit of a diagram to explain it properly. Here is a lovely diagram of the curve y equals sine x and the line y equals x. You may have already encountered this property in class before, but what we're seeing here is that as we get really close to 0, the curve y equals sine x becomes very, very close to the line y equals x. They're only ever going to cross over at the point here. Everything to the right of 0, the blue line is above the red line. So from this, we can form the inequality that sine x is less than x whenever x is positive, and we can turn this into the variables that we're dealing with by saying sine 2ka is less than 2ka when we're dealing with positive values. Now, what I can do with that is I can go to my expression for k and I can change the bottom to be 2ka. And so because that's going to make, because this one is smaller, making that change is going to make this one larger. Okay, so changing the bottom of the fraction to a larger number is actually making the fraction smaller. So we have k is greater than 2a over 2ka. Now that's the really clever part that took me a while to see, because now that we've got this inequality, this part really tidies up quite nicely, because the 2a's are going to simply vanish away through the power of division, and we end up with k is greater than 1 over k, and then we can just times the k across here and get k squared is greater than 1. And now the only time you're squaring a number and getting an answer bigger than 1 is when the number itself is bigger than 1 or less than -1. But as the question said all the way back 5 minutes ago, k is positive. So the only positive solution to this equation is that k is greater than 1. And that right there is our 4 marks in a Band 6 question from the 2024 HSC exam. So I've found a few different solutions for this question online, and this is the one that really made most sense to me and I could follow more logically. So hopefully that made some sense to you. If it didn't, again, comments, bullying, you know what to do. That will do it for today's video. Hopefully you got some value out of that and help build a bit of confidence with tackling some HSC exams. If you did get some value and appreciate the hours that I spent making this, maybe consider liking and subscribing while you're here. And if there are any more questions in the 2024 exam that you want some help with, you can flick me a DM on Instagram and I'll help you out whenever I have the time to. But that's all for today. Thanks for watching, and I'll see you soon for some more extension content. Bye for now, not forever.